Hello, welcome to my first video. So in this video, we're going to talk about techniques with integration, but dealing with a indefinite integral. So the first thing that comes to mind, usually there are so many techniques, but in this situation, we're focusing on a thing we call integration by parts. So the way you know you're using integration by parts is usually you're going to have an integral. So usually you have an integral that we just don't know right off the bat by just looking at. It's filled with all this madness, and we're like, how do we find an antiderivative of this? So I want you to first notice for this example, we have the integral of x times e to the 2x. And please excuse me, and there should be a dx here because we have to be able to integrate. So the first thing you always think about with integration by parts is I have two functions inside of my integral. And the idea is that we like to use these little letters u and v. So the idea is you have two functions. So I'm going to highlight these in different colors. So I want you to notice you have a polynomial and you have a exponential. So the idea is when we're dealing with integration by parts, we usually are going to let u be one of the functions, and we'll call that function f of x. And then we try to find the derivative of that specific function we're letting u be, that's inside of the integral, and we write that one as f prime of x. So what the dv, so then you have a thing we call dv. And what the dv represents, it's going to represent what's left over in the integral. So dv, so when you think of dv, think of it as the integral of the function you didn't let u be, which is inside of your integral. So we call that one g of x. So when you find the antiderivative of that, we call it a bit g. We just let it represent bit g of x, and that's the antiderivative of what's left over. So, and we're gonna apply the same method, but we're just taking it step by step, building up to that. So you let u be one of the functions inside of your integral, and you find the derivative of that. And then you let dv represents the integral of what you didn't let u be. And then when you find v, that's the antiderivative of that. But now you're asking yourself, how do I even know what to let u equal? So let's, I have a little trick for that. In general, I like to call it, we call it lopti. And now we're saying, whoa, what is lopti? So when you think of lopti, it's every function you can think of that's inside of your integral. And the idea I'm going to have you see is, all right, so the L stands for log. The A stands for inverse. Okay? P stands for polynomial. T stands for trig function. And E stands for exponential. So the idea here is you try to see what functions do I have inside of my integral. So for one, we have a polynomial, right? And we also have a exponential. So now you say, well, which one comes first in this pattern of letters, lopti? So we will note that the polynomial here, so p, comes before e. So for this example, usually you kind of use these type of, because there'll be examples of integrals where it doesn't matter which one you let it be, but in the polynomial case, you'll usually use this little method here. So I see that polynomial comes before exponential. So in general, my f of x in this case, well, whatever we're saying, let u be. So this, so in general, we're saying let u equal x. That's how you determine when you're dealing with polynomials and exponentials and trig. It's a little method you can use. So this is how we get to that generation that, oopsie. This is how we, oops, it keeps deleting that. So in general, what we want to say is here, u is x. My little eraser. So in general, this is how we come to the conclusion that u is x. And since I know that u is x, remember I said dv is going to represent the integral of what you didn't let u be. So essentially, your g of x in this case is the integral of e to the 2x. Because we didn't let u be that. So that represents what dv should be. So now we have that dv is the integral of e raised to the 2x. And then what we have to do, we have to find, the next step is when integration by parts, you have to find du, and then you have to find v. So du is just the derivative of u. So here, the derivative of x is just 1 dx. Using our, and we want to put a little side note, whenever we have something raised to a power, now that's not, so this is not antiderivative, this is just to put a note there. Whenever we take the derivative of a polynomial, whatever power is raised to, you bring down, and then you do, and you subtract 1 from that power. So essentially it's imaginary 1 here. So that's 1 times x raised to the 1 minus 1. But, and we got a dx here. Just kind of showing what's happening. Just to give a little refresh just in case. So this actually is just 1 times x to the 0 power dx. And recall, anything raised to the 0 power is just 1. So this is 1 times 1 dx. And 1 times dx is just dx. So that was just a little refresher for using your power rule. So in general, the derivative of x is just dx. And you have to find, so now when you think of v, you're actually finding the antiderivative because we have something in our integral here, which is left over. So another little note I want to give you is, put a little side note here, is whenever you're trying to find the integral of e, please excuse my dog, when you have a integral being raised to any type of function, so I want you to think of whatever is raised to e is a function that it's raising. So imagine that is, we'll call it h of x, because I don't want us to, because sometimes using the same letters can get confusing. So what I want you to think about here is the antiderivative of e raised to any function is always going to be itself. So e raised to the h of x divided by the derivative of what it's raised to. right? So this is a little thing to add in your notes, and just in that case. And so when you notice that is, so now I want you to think of that 2x here in our integral. E to the 2x is like your h. So in general, the antiderivative would just be e to the 2x divided by the derivative of what it's raised to. The e is raising 2x, so the derivative of 2x is just 2. And look, there's your v for you. And now the definition of integration by parts, when we want to write integration by parts, it's always written in this form. So it's always u times v minus the integral. So let's kind of put a little red line over this, put this kind of in a box. V du. So the tricky part is kind of finding what you should let u be. And one thing I want to point out is, notice when we took the derivative of u, that power is decreasing. If you had let dv be x, well, we would have been increasing the power on the polynomial. So I'd say a little tip is, when dealing with polynomials and using integration by parts, usually what's happening, usually you want to let u be that, because what happens is you want it to keep going, you want the power to keep going down until you just get 1 dx or whatever the constant is. But sometimes you'll have to do the integral 2 times, but essentially I'll be doing examples like that too. But for this one, we're doing just kind of taking it step by step here. That's just one thing I wanted to note there for you. And now all it matter is now is just substituting and trying to see how we can keep simplifying it. So now we just substitute. So u was equal to x, right? So we're substituting. So this is x times, what did we say v was? It's e to the 2x over 2. Then we have minus the integral of v. And v again, we said, well, v is e to the 2x over 2. Okay. And what is du equal to? Just dx. We're almost to the finish line. Almost to the finish line. So note we have integral, another integral, but this should be the last one we have to evaluate. And the good thing is we don't have to use integration by parts, because notice it's only one function inside of this integral now. One specific function. But let's kind of put in our notes is, whenever you have so most times we like to bring out the constant. So when you have a constant, and since we're using c, let me use, let's call it d, because we have to use c, right? Because whenever you have an indefinite integral, there's always a plus c. But this is a general constant multiplying your function. You can always pull it out, and then you can evaluate not evaluate, but find the antiderivative afterwards and you just multiply the constant later on to that specific antiderivative. So notice I have e to the x over 2. I can rewrite this the same form we have here. So uv is fine. That is as simplified as that can get. That's fine at the moment. Oopsie. I was supposed to And so yeah, so that's e, and then we have this e to the 2x divided by 2 minus, now I'm going to pull out 1/2 out of the integral because it's just a constant. And that just makes it easier on the eyes to see what the antiderivative is just by looking at it. Make it a little easier. Okay. Oopsie. So we get the integral. So just notice this minus 1/2 is it's multiplying the integral here. Just don't forget that constant has to multiply later on. And notice this is just e to the 2x and we have dx, right? And look, it's just another integral. We have already taken the integral up. So essentially, you can actually leave this in, I would say we could put it in parentheses or we can distribute later. So now when you come to what this should be, again, recall we found the antiderivative of e to the 2x here. So the antiderivative of e to the 2x is e to the 2x over 2. But it's going to be plus c in this case because we got to the final integral and we're dealing with an indefinite integral. So essentially, this whole integral is equaling, the antiderivative is this entire thing, but we have to find the antiderivative of e to the 2x. So again, this becomes x times e to the 2x divided by 2 minus 1/2 and just recall the so I'm putting in parentheses here. Usually we'll use a bracket, but I put a parentheses here just to let myself know, well, I haven't distributed the -1/2. So again, we said the antiderivative of e to the 2x when you find that antiderivative, it's e to the 2x over 2. And just remember, indefinite integral, you always have a plus c. So this becomes plus c. Okay, and I have one little typo here. I'm just filling in from the video. I had all of this plus c, so plus c should be separated on this piece of the end when we distribute. So then what it looks like when we try to rewrite that, we should have something like this. And the very last part is going to be x times e to the 2x over 2 minus 2 times 2 is 4, e to the 2x plus c. This is our final answer. I do apologize for my typo there. So the integral of x e to the 2x is essentially the indefinite integral is this guy. And I will also put one, this is just using integration by parts just to get you into the feel of using it, because they may one can say use integration by parts to solve this, or they may say just use techniques. You could also use u-substitution, which would be a quick one too, but I just want to show first integration by parts. It's a similar way you can get the same answer.